So I would like to call upon our first speaker, Mr. Eduardo GUENDELMAN, to present black holes and child universes. Thank you.
Okay, it's a pleasure, and I'm very grateful for your invitation. Actually, I should say that one of the other students of Alan Bus, Gemal Guven, he was also from North Cyprus, a very good friend of mine. So I'm going to tell you about black holes and child universes, and so a little bit of the history of black holes, what is a black hole, and then very crucial for the subject of the child universe is that the black holes appear to be to double the space-time. This becomes the crystal extension. Then the role of the child universes, this crystal extension, how to build a false inflationary vacuum bubble with a black hole exterior, and how this relates to child universe. I may talk about, if there is time, I'm not sure, probably I have to cut a little bit, about some subtleties, and then make an over. Okay, what are black holes? Black holes, very long time ago, people started to think about black holes, postulated that there are objects where the escape velocity equals speed of light, and these are black objects. Okay, so this was very a very rough idea, but actually it got was a very helpful insight. But it was not until in the 20th century, when the general relativity came, that we really started to understand what is black holes. Understand from general relativity that gravity is not a force, but is the curving of space-time. Matter moves in a straight line through curved space-time. This is geodetics, right? Using geodetics. And the energy, the amount of curvature is determined by the matter energy that resides in some place. And then there's a curved space-time tells us how matter moves, and matter tells us how space-time, how much it should curve. Then there was the discovery of black holes, although it was not understood completely. But there was this Karl Schwarzschild in 1915 used the Einstein equation and found almost immediately after general relativity was formulated, found the famous Schwarzschild solution. Now we call it the Schwarzschild black hole. At the beginning it was just called Schwarzschild solution. And it gives us the metric of the black hole, and has this was not discovered, it was not understood by Schwarzschild, but we understand now that there is a horizon. At the time Schwarzschild found a singularity here, but now we know that there is not a singularity, a horizon instead. And there is a singularity at r equals 0. Interesting that Schwarzschild wrote this in the World War I. And he volunteered to the army, and he was over 40. He died a few months after the publication of this very important paper from a rare skin disease that he contracted in being in places like this. So what are the properties of the black hole that are going to be crucial to our discussion? Is that, as I mentioned, the black hole has two bad places, right? The singularity at article 0 and the event horizon. As I mentioned, Schwarzschild didn't understand the event horizon. Even Einstein didn't understand. It took a long time for understanding this. Einstein wrote some paper that thought that this was a real singularity, but now we understand it is the horizon, not the singularity. This event horizon, as we understand now, is not a bad place, in the sense that can be crossed without problem, and one can live to see the other place. But it is a point of non-return. So if you cross it, you will get to the singularity. Not even light can escape once it goes from here. So the observer who crosses the event horizon eventually ends up at the real bad place, article 0. On the trip to article 0, the observer still become spaghetti at some point. The observer, because of the tidal forces, become very strong. At article 0, they become infinity. The observer cannot avoid ending at article 0 any more than we can avoid encountering next Monday. Space and time switch roles. The radial coordinate become a spatial coordinate, and the spatial coordinate becomes. Now, whether you don't have to pay so much attention to the formula, but the equation of the Schwarzschild solution is the Schwarzschild. The way he found it was a metric. The metric defines the space-time, and there is this horizon here. R equals 2gm, and you see here, this becomes 0, and this becomes infinite. And at R equals 2gm, you would think it is a singularity, but it is not a singularity. Kruskal and Sekeres found a new metric, and by the way, double the space-time in doing so. So you start with this set of coordinates. You see that when R is smaller than 2gm, this becomes, this first of all, at R equals 2gm, this becomes 0, and then it changes sign. So this T becomes a spatial coordinate, and R becomes a time coordinate. So these people, Kruskal and Sekeres, made a coordinate transformation for the region bigger than 2gm, outside the horizon. They made a coordinate transformation. Doesn't matter exactly what it is. Then for the region small, you have this other coordinate transformation. So they found that the region 1 and region 2. But they found that they found that you can extend. This is by itself not the whole space-time. There is 1 and 2 are, you would think, a radius outside the horizon. The horizon is this line here, R equals to M. The inside the horizon is region 2. But suddenly they found, oh, there is region 3 and region 4. Oh, it's nice. Black hole. Yeah. Then there is R equals 0. There is also another R equals 0. There is a region 1, region 2, and then there is a R, which is these are coordinates called V and U, and R is the function of U squared minus V squared. So the same R that is here. So the space-time is doubled. Space-time is doubled. And then you have what is called a wormhole. If you look at the radius as a function of U, yeah, radius as a function of u. The radius becomes has a minimum here and it grows. So there is r going to infinity in this place, when u goes to infinity, and r goes to infinity when u goes to minus infinity. So there's a double of space-time, doubling of space-time. And this is the notion of wormhole. This is going to be very important. And so as you see, in terms of this coordinates u, v and u, the space-time is perfectly regular. At r equals to n, nothing happens. There is a constraint that, as I mentioned here, r is a function of u and v. This is a transcendental equation. And this is just the space-time, the current transformation in each of these regions 1, 2, and then we found the extension to 3 and 4. Now we go into the subject of how this connects to inflation, inflationary bubbles. So what is the inflationary scenario for cosmology? It's based on the assumption that somehow the universe started not in the ground state, which we are now here, or close to here, we are here. So for simplicity, you say that here this is a zero energy density. The vacuum, the real vacuum is here, but the universe instead, in the early universe, started at some point here with a high energy density, right? So there is a vacuum here that is not the real minimum. So this we call a false vacuum. So this one is there representing the false vacuum. Here is the true vacuum. Schwarzschild solution, for example, will live here. And inflation, Booth and others tried to connect this false vacuum to the idea of inflation. This, if you insert this vacuum energy in the Einstein equations, has a property that the pressure equals minus the energy density, and this produces inflation, phenomenon by which the universe is driven by exponential expansion, caused by the repulsive false vacuum. But notice that this here is also has negative pressure, very interesting. But this causes the gravitational effect of exponential expansion. Now we want to connect these two spacetimes, and this brings us to the dynamics of false vacuum bubble. So suppose that we are here in some spherical bubble, and the outside of this bubble is here. And then you have a bubble, and then you ask for the dynamics of this bubble. So let's consider a spherically symmetric universe which consists of a region of false vacuum separated by some domain wall. The domain wall is called this bubble wall. The thickness of the wall we assume very small compared to the radius of the bubble, right? So the interesting thing is that here we have true vacuum. The true vacuum has no energy density, no pressure, nothing. The pressure is zero. Inside they have a negative pressure and positive energy. So you want this fellow to inflate, because this Einstein equation, if you didn't consider that there was a boundary here, Einstein equation tells you that this has a exponential inflation. That's called the inflationary scenario, right? That in the early universe everything expanded exponentially. However, how can this expand when the pressure outside is smaller than the pressure inside? Here the pressure is negative, and here the pressure is zero. So the pressure should force the bubble to go inwards. We will check, however, that the bubble can still expand, and this is very much related to this wormhole. The evolution of the bubble can be described by some function of the radius of the bubble, which is the 1/2 pi times the circumference, right? Circumference 2 pi times the radius. So in order to solve this problem, the space-time has to be divided into 3 regions. The exterior region, spherically symmetric, empty space for which there is a unique solution in general relativity, which we have seen before. This is the Schwarzschild metric. The interior solution consists of a spherically symmetric Hopf vacuum, is regular at r equals 0. This is the unique solution, is the Sitter space or inflationary space. The interface is a domain wall. So we use the Einstein equations, or not it's something that depends on the curvature, something depends on the matter content. In the false vacuum, we have this. In the true vacuum, the Schwarzschild, we have zero energy momentum tensor. And we define some vector field that points from the Sitter to the Schwarzschild space. The positive region is the Schwarzschild space, and the negative. So we have to use the UV coordinates, and let's go now to the describing a little bit what is the Sitter space. The Sitter space has a similar feature to the Schwarzschild space. Can be described like this, and times the inverse, as that. So you see there is a horizon also. There is at r equals 1/chi square, there is a horizon. The Sitter space has the feature that you define this for a particular center. Any center is okay, you can define this. The horizon has the opposite feature of the Schwarzschild. When you are outside the horizon, you must expand and never return. So it's a repulsive space instead of a attractive space. And you do the same trick that we did for Schwarzschild. You define a change of variables, change of coordinates, and you find a space like this. These are the Gibbons-Hawking coordinates. So there's the horizon. The horizon, instead of r equals 0, which was the end value of the. If an observer crosses here, instead of falling into r equals 0, it has to expand to infinity, repulsive space. Okay, this is again the relation between the u and v coordinates. We don't have to go into the details, just to know that there exists such a thing. And then the motion of the bubble, because there is as I mentioned before, right? There is a bubble that moves, that defines the separation between the inside inflationary picture and the outside. This moves. So what is how do we determine the motion of this bubble? It's like the difference of two what we call extrinsic curvature. It's like the analog of the in electromagnetism, the discontinuity of electric field is determined by the surface charge, right? The analog, instead of electric field here, you use extrinsic curvature. So you calculate extrinsic curvature in Schwarzschild minus extrinsic curvature in the Sitter, and it's determined by the surface tension of the bubble. The surface tension of the bubble. And as I mentioned, this is the gravitational analog of the equation in electromagnetism that the electric field has a discontinuity of 4 pi sigma. You can see even 4 pi sigma here. But here this sigma is the surface tension, right? And you have an equation that, for example, calculating the discontinuity of theta theta, you have an equation that relates the mass of the object to the velocity, all kind of things like that. You define all kinds of quantities, right? And you find that the motion of the bubble, you define this z is like a rescaling of the radius with some constant here. The motion of the bubble and this tau prime is a rescaling of the proper time. It's like defined by equation of like a particle in a potential. This is like the kinetic term plus potential term plus energy. The energy is the mass, depends on the mass. You have a potential here. And then you can see that there is a potential here, right? A potential. If you have enough energy, you can start from r equals 0 and extend to infinity. If you don't have enough energy, you can get to some maximum and then return. It's like a, right? And so there are all kinds of possibilities. But then we go back to the question, the original question. How is it that this guy is going to expand to infinity, right? If the pressure outside is bigger than the pressure inside, that doesn't make sense apparently, right? Here. However, if we draw this the motion of the bubble in the Schwarzschild space time, this is the Schwarzschild space. We cut a little bit of the Schwarzschild space to make for the de Sitter region, and make slices, all kinds of slices, A, B, and make a picture of these slices. We saw here the radius. The radius is you see here the radius here and the radius here is the same. So this is the picture, the geometry of a wormhole. We can for example, this here will correspond, this A will correspond to a picture like this. We don't even see the Sitter space yet. Here we see a little bit of the de Sitter space, and here we have already in C we see we start to see this wormhole. This here is the same as this here. Yeah. We see this wormhole here, and finally there is a disconnection between the ambient space. And this can expand as much as you want. And so a nicer picture is like this. And you have here the false vacuum is doing like this. This arrow here is the direction of the force. The force is determined by difference of pressure. So the difference of pressure is from the outside, in the direction from the outside to the inside. So this tends to contract the bubble, right? However, what happened here? The direction of the force is still from the inside, from the outside to the inside. But inside to outside is direction, here is the force is from direction of decreasing radius. So the force forces the bubble to become smaller in radius. Now, because of the wormhole geometry, the force is from outside to inside, but this is not direction of a lower radius. It forces the bubble to expand, and this is like if you want, like a cosmic judo, right? What is the judo? this force is trying to kill the bubble, to make it collapse. But the wormhole changes this everything, because the direction from outside to inside, now it's a direction of increasing radius. It forces, so we may call it a cosmic field. And then there is this connection. This kind of picture that the force is acting like this is in some sense related to the fact that this wormhole has a negative energy, a negative gravitational energy. So this universe can become as big as you want, and the conservation of energy is not violated because the wormhole is going to compensate the very big positive energy of the whole universe, in almost arbitrarily large, with the negative gravitational energy of the wormhole. Yeah, I don't know how we're doing time. 5 minutes. Okay, so I'll just put up the picture, and then I'll just go through some potential problems that maybe not all of them. There are some problems with this picture, because you can say, is it possible to create the universe in the laboratory? The answer at the classical level is no, because there is an initial singularity. You saw that this here, we have here initial singularity here. Right? So this was shown that it would be a regular, there's a singularity theorem that if you don't violate the energy conditions, that's the catch. That you can have a creation of universe, you can violate the energy conditions, or you can go to quantum theory. And here your North Cyprus colleague, Ruben, worked also with Farhi and Woos, and studying a bubble that classically it will not be able to make a universe, but because of quantum tunneling, you can inflate to infinity. And there are other ways to address this problem. Instead of a positive energy surface tension, you add some kind of contamination to the bubble of dust, which has a surface density which is negative. And then you can see that the bubble can be oscillating between these 2 points. And then if it emits an energy, this barrier here goes up and this goes down, and the universe can escape to infinity. You can have a creation of a bubble of a child universe in this model. Other subject is that, as I mentioned here, the bubble, the wormhole has negative positive energy. So you can have very high ultraviolet excitations with very high surface tension, very high bulk energy inside the bubble, and the critical mass here that I have calculated here. Actually, when this energy density goes to infinity, this goes to 0. So you can have a very high energy bubble that is 0, and then there is some model with a string surface that you can have a universe that actually you can build out of zero mass. So let us summarize, and then Zeya will say something more about this. So child universe can have a non-singular origin, avoiding this theorem, by allowing a negative energy component, as in the model of breeding. There is the model also of originating the universe from quantum tunneling. For very high energy densities, you can have a creation of a universe with a unsuppressed barrier, because the critical mass goes as the inverse of the density of the bubble, the energy density that you are making. So this could provide a mechanism by which high energy densities could disconnect from ambient space. And then you get rid of high energies, very high energy densities in quantum gravity maybe, and regularizing quantum gravity. So in conclusion, the study of child universe could have implications from our understanding of our own universe. Importance may be important in the understanding of the ultraviolet structure of the quantum gravity. Okay, that's up to here.
Any questions? About the bubble itself, you mentioned the discontinuity of extrinsic curvature.
Yeah.
The energy, the surface energy and the pressure on the bubble, how about them? Do they satisfy energy condition? I mean, the bubble.
Yeah.
itself-
The problem I mentioned is that the problem that we solved originally was for sigma positive. Yeah. So this picture here is for positive surface tension.
Okay,
And it began with the singularity because of this term.
so I'm not talking about sigma positive. I'm talking about the energy condition. I mean.
The energy condition is the only place that you have matter is in here, the Situ space with the positive energy and the surface of the bubble. They both satisfy.
What about the pressure of the bubble? I mean, the pressure
Yeah.
on the surface.
Yeah,
On the
it's
surface.
a surface tension.
Yes.
Yeah, it's
Is that positive or negative?
positive.
Peak energy is satisfied.
Hmm?
Peak energy condition.
Yeah. Yeah, it's like a soap bubble, right? It has a surface tension. Yeah, this is no strange limit.
Understood.
The strange thing is the crystal, the wormhole. Yes.
What is an anti-trap surface exactly?
What is
Anti-trap surface.
anti-drop surface? Yeah, it's yeah, this is like yeah, well, it's like you are inside the horizon. But you must go into the horizon. It's a condition for collapsing. Here you see that here you have trap surface is like a time reversal of the trap surface is the thing that you are need for gravitational collapse.
Okay.
Then you collapse. Anti-trap is the time reversal because this here is the black hole. You see that the critical solution has a black hole, but this here is what's called a white hole. So the white hole is the opposite of the white hole is the opposite of the black hole. Right? For the black hole, you study conditions for collapse, which are the trap surface. Right? That you are here entering the horizon, you are trapped, and then you collapse. Here is the anti-trap surface. So you are using the singularity theorem in a time reverse way. Because here the singularity theorem is that you go into the future singularity. Here is like the Big Bang singularity. So it's anti-trap. As I mentioned before, we had the condition that everything here must collapse, right? That was the original idea. And here everything must explode. Yeah, go out of the horizon. Yeah.
Somehow outgoing surface.
Outgoing. Yeah, this is the a singularity. The R equals 0 here is like a Big Bang. This is like a local Big Bang, right? And well, so in any way we get back to the Big Bang, but in a local way instead of a global, right? The usual cosmology is a Big Bang everywhere in space. Here is the Big Bang at the point. This is the white hole.
If there is no any question, let's go.
Thank you very much.